If you're confused about radicals, this is the video for you. We're going to talk about how to simplify square roots as well as cube roots. I'm going to give you a couple different options. You can pick the one that you like better to work with. We're also going to talk about how to multiply radicals, divide radicals, rationalize radicals, add and subtract radicals. It's a complete guide, so I'm going to take you through this step by step. We're going to go through 20 examples. Follow along. You can even pause the video and practice if you want to test yourself on some of these problems. Let's get started. The first one we want to look at is the square root of 48. Okay, so how do we simplify this square root of 48? Well, square root is basically asking us what number times itself is equal to 48. Well, you can see here, you might want to write down this list here. I wrote down the perfect squares and the perfect cubes. So you can see like 4 squared is 16, 4 cubed is 64. But what number times itself is 48? Well, 7 times 7 is 49. But you can see this is not exactly a perfect square. So what do? Well, we're going to try to divide out perfect squares. And the way that you can do that, option number one, is you can look down this list of perfect squares here, and you can say, do any of these numbers go into 48 evenly? Now, you could pick, let's say, for example, 4 goes into 48. So I could write this as square root of 4 times square root of 12. Then when I look at 12, I can say, are there any perfect squares that go into 12? Looks like 4 goes in there again. So instead of this 12 here, I'm going to write this as square root of 4 times square root of 3. That's equal to 12. And I'm going to bring down this square root of 4. Can I pull out any additional perfect squares? Doesn't look like it. So now I say, well, what's the square root of 4? Meaning what number times itself is 4? That's going to be 2. Again, what times itself is 4? That's 2. And we multiply these together. 2 times 2 is 4. Square root of 3, this is kind of like your remainder. You can't really pull out another perfect square out of 3. So we're just going to leave it like that, and you got it. Now that's option number one. Option number two, you can do a prime factorization tree. So what you do is you break down this number into its prime factors. So I'm just seeing what this number is composed of. Then I look at all the ends of the branches here, and I look for 2 of the same number. Not necessarily the number 2, but a pair of the same number. If it was a cube root, I look for 3 of the same number. A fourth root, I look for 4 of the same number. So for example, this is a perfect square, this is a perfect square, and I have a 3 left over. So for each group, I get one of this quantity. I get 2 times 2, which is 4, and I have 3 left over. So this is 4 square root of 3. Same thing we got over here. Now, why does this work? Well, you can see you have 2 of the same number. That's like 2 squared. When you take the square root of 2 squared, the square and the square root, those are inverses, and so you just end up with 1 of that quantity, 2. Same thing here, 2. 2 times 2 is 4, and then we have a 3 left over. Now, what happens if there's a 3 and say like a 5 left over? We'd multiply those together and we'd have square root of 15 left underneath the square root. So let's go and do another example. Let's take a look at square root of 150. So 150, are there any perfect squares that go into 150 evenly? Well, it looks like 25 would go in there 6 times. So I'm going to write this as 25, square root of 25 times square root of 6. What number times itself is 25? That's 5. And we have the square root of 6 left over. Now you can see, are there any perfect squares that go into 6? Well, you can see 4 doesn't really go in, 9 doesn't go in, evenly. So you can see this is like the remainder. Now that's option one. Now option two, we can do a prime factorization on 150. Let's break that down. You could do 15 times 10. 15 is 3 times 5, and 10 is 5 times 2. Because we're taking the square root, we look for 2 of the same number. You can see we have 2 5s here. So that's going to come out in front of the square root. And we have a 3 and a 2 left over. We're going to multiply those together. That stays underneath the square root. And you can see we're getting the exact same answer, 5 square root of 6. Okay, so for example, number 3 and number 4, we've got some variables now that we're working with. So let's take a look at number 3. So we're looking for perfect squares we can pull out of 54. I know that 9 is a perfect square, and 9 goes into 54 evenly. So we could write this as 9 times 6. X squared is a perfect square, because x times itself. And then y to the 5th, I'm going to write this as y to the 4th times y to the 1st. This is a perfect square because y squared times itself. Y squared times y squared is y to the 4th. So now if we simplify, square root of 9 is 3. Square root of x squared is x. Square root of y to the fourth is y squared. And then we're left with 6y underneath the square root. That's like our remainder. Now, in this particular video, we're assuming that all the variables are positive. That's how a lot of students approach this, a lot of teachers approach this at kind of a basic level. If you're doing this at a more advanced level, when you're taking the even root, like the square root, fourth root, sixth root of an even exponent, okay, like this, a variable with an even exponent, and you end up with an odd exponent, like here we have x to the first, you have to put that quantity in absolute value bars to ensure that it's positive, okay, the outcome is positive. If you're not learning at this level, just ignore that for now, but if you're, just remember, if it's an even root and you end up with of an even exponent and you end up with an odd exponent, you're gonna have to put it in absolute values. Now this is option one. Option two is we can do the prime factorization tree. So we could break down 54 into its prime factors. So 9 times 6, 9 is 3 times 3, 6 is 3 times 2. And then because we're taking the square root, we're looking for a pair or two of the same number. So here's a pair. So that would be 3. And then 3 times 2, that's left over. That stays underneath the square root. Now, x squared y to the fifth, you can think of this as x times y times y times y times y, right? So here's a pair, so that would be x. Here's a pair, that's y. Here's a pair, that's y. Y times y is y squared, and then we have this y left over, that stays underneath. Again, you can do the absolute value thing that I was showing you earlier if you're learning this at a more advanced level, or you could just leave it without that if you're assuming all the variables are positive. And you got it. So a couple different options. Let's look at another example. Number 4 now. Let's see, are there any perfect squares that we can pull out of 288? Well, I can see that 288 is actually 144 times 2. 144 is a perfect square because 12 times itself. A to the 7th, I can write this as a to the 6th times a to the 1st. And then b to the 8th, I can write that just as b to the 8th. This is a perfect square because b to the 4 times itself. B to the 4th is b to the 8th. So if we simplify, square root of 144 is 12. Square root of a to the 6th is a cubed. Square root of b to the 8th is b to the 4th. And then we're left with square root of 2a. And you got it. Now, here we don't have to put any absolute value bars because a to the 7th, that's an odd power. So you can't take the square root or the even root of a negative number. If a was negative, a negative to an odd power would be negative, and you wouldn't be able to take the square root. You'd get imaginary numbers. So because we have here in our answer a to an odd power, this has to be positive because otherwise here you would have an issue. You only have to put the absolute value bars if you're taking the even root of an even exponent and you end up with an odd exponent. Then you have to ensure that it's positive. So this one's good, but the option number 2 is to do a prime factorization tree. So we can take the 288, break it down. We can see that this is 2 times 144. 144 is 12 times 12. 6 times 2, 6 times 2, 2 times 3. Break it all the way down to the prime factors and then look for 2 of the same number. So you can see here's a pair of 2's, here's a pair of 3's, here's a pair of 2's, and we have a 2 left over. So for each pair we get 1. Remember, so we have 2 times 3 times 2, that's 12, with 2 left over. And what I like to do when I have a higher powers, what I like to do is I like to say, how many times does 2 go into 7? It goes in there 3 times, so that's going to be a cubed with 1 left over. How many times does 2 go into 8? 4 times, so that's b to the 4th with none left over. And you can see we're getting the exact same answer as we did here. When you take the square root, they don't write this index of 2 here. It's understood to be a 2. When we get to the cube roots, you'll see that there's an index like 3, 4, 5, depending on what root is. Square root, they don't write that, it's understood, but that's what I'm doing is I'm seeing how many times does 2 go into 7, how many times does 2 go into 8. It's a shortcut. The other way to do it is you could write it out, a to the 7th, a 7 times, and then circle groups of 2. But as these get higher and higher, that's going to be kind of time consuming, so you might want to just make how many groups of 2 by dividing that in. Okay, now for number 5 and number 6, we're going to talk about cube roots, and we're going to do the 2 different options, so pick the one that you like the best. Cube root of 48 now. We did square root of 48, but for cube root of 48, we're looking for perfect cubes that go into 48. So I'm looking at this third column here, and I say, well, what goes into 48? Well, it looks like 8 will go into 48 6 times. So this is going to be the cube root of 8 times the cube root of 6. And are there any perfect cubes that go into 6 evenly? Doesn't look like. Well, 1 does, but 1 times, that's not really going to simplify it for us. So cube root of 8 is just going to come out to 2, because 2 times 2 times 2 is 8. And then we're left over with this cube root of 6. The other option is to do the prime factor tree. So we're going to break this down. You can do it, let's say 8 times 6. 8 is 4 times 2. 6 is 2 times 3. And 4 is 2 times 2. Now, because we're taking the cube root, we're looking for groups of 3 of the same number. There is a group of 3 with a 2 and a 3 left over. So for each group here, this is really like just going to give us 2. And we're left with 2 times 3, 6. That stays underneath the radical. So again, this is really like 2 to the third power. And when you take the cube root and the cube power, those are inverses or opposites. They cancel. That's why we're just getting 1 of this quantity, just 2. Okay, so for number 6, let's try this one, the cube root of 54. 54, are there any perfect cubes that go into 54? Well, if I look at this third column here, it looks like 27 goes in there 2 times. So 27 times 2 is 54. And the cube root of 27 is 3, because 3 times 3 times 3. 3 to the third power is 27. And we're left with this remainder, cube root of 2, and you got it. So that's option 1. Option 2, we can do our prime factorization tree. 9 times 6 is 54. 3 times 3 is 9. And 3 times 2 is 6. Now we're looking for groups of 3 of the same number, not necessarily the number 3, but 3 of the same number. And that's going to give us 3 with a 2 left over, 3 cube root of 2. And you got it. Again, remember, for each group, you just get 1 of that quantity. Now, if I had a group of 3s and a group of 5s, I'd have 3 times 5 would be 15 on the outside. Or if I had a 2 left over and a 7 left over, I'd multiply those. That would be 14 that would stay underneath the cube root. Okay, for number 7, we're taking the cube root now of 288, a to the 7th, b to the 8th. So you can see we've worked with some of these quantities before, but now we're doing the cube root. So are there any perfect cubes that go into 288? Now 288 is kind of a big number. Now you could try using a calculator and see if any of these go in. Okay, that's one option. But when it's a big number like this, sometimes I like to just go right to the prime factor tree. I can see exactly what 288 is made up of. So let's go ahead and do that. So this is really 144 times 2. And we know 144 is 12 times 12, and 12 is 4 times 3, and 4 is 2 times 2. Now, because we're taking the cube root, we're looking for 3 of the same number. So it looks like we've got 3 2's here, and we've got a 2, a 2, a 3, and a 3 left over. So it looks like only 1 2 is actually coming out here. Okay, and we're left with 9 times 4 is 36 left underneath our cube root. And let's see, a to the 7th, 3 goes into 7 twice with 1 left over, and 3 goes into 8 twice with 2 left over, and you got it. Now again, you can write out a to the 7th 7 times. It's just that this takes a little bit. Then you make groups of 3. A times a gives us the a squared with the a left over. That's another option. So that's one way to approach it. So let's look at number 8. So now what we're getting into is radicals of like quotients. So when you're dividing or you have fractions. So how do you work with something in this form? Well, you can see this is a square root. When we have a fraction, what we can do is we can split this up into square root of the numerator over square root of the denominator and treat it like 2 separate problems, the top and the bottom. So what number times itself is 16? That's 4. What number times itself is 9? That's 3. And we simplified it, 4/3. Okay, for number 9, we're working with the cube root of 27 over negative 8. So again, like we did in the previous problem, we can split this up into the cube root of the numerator over the cube root of the denominator. And then you just do them individually. What number times itself 3 times is 27. That's going to be equal to 3. What number times itself 3 times is negative 8. That's going to be negative 2. And you can take the cube root of a negative number, you just can't take the even root of a negative number, like the square root, the fourth root, sixth root. Negative 2 times negative 2 is 4, times negative 2 is negative 8, and you got it. Now for number 10, we're taking the cube root of a fraction, but we've got some variables involved. So how do we work with this one? A couple different options. You can split it up like we did with this last problem. You can also try to reduce what's underneath the cube root first and then split it up. So in this case, I can see 128 divided by 64. That's really the same thing as the cube root of 2, a to the 5th, b squared. Now I'm looking for groups of 3. There's not a perfect cube that I can pull out of 2, but I'm looking for groups of 3, so I can see, 3 goes into 5 once with 2 left over, so that's going to be a squared, and then 3 goes into 2, no it doesn't, so that's going to stay underneath the cube root. 2, we couldn't pull out a perfect cube, so that stayed underneath, so that's as far as we can go on that one. And then for number 11, now what we're getting into is what's called rationalizing denominators. And what does that mean, rationalizing denominators? Well, the square root of 3, this is irrational, meaning it can't be written as a ratio, but an integer over an integer. It's an irrational number. We don't want that radical in the denominator. That's considered improper. So how do we eliminate this radical in the denominator? Well, if it's a square root, what you can do is you can just multiply by that same square root to the numerator and the denominator. And the reason this works is because square root of 3 times square root of 3 is square root of 9, which the square root of 9 is just 3. And so we've eliminated that square root in the denominator. 2 times square root of 3 is just going to be 2 square root of 3. And some people make a mistake. They might write this as square root of 6, or they just write it as 6. And let's just talk about that for a moment. When you multiply numbers, this is what we've been doing since elementary school, right? 5 times 7 is equal to 35. But if you multiply a square root times a square root, you just get square root of 35. You just multiply what's underneath the square roots. If you multiply, let's say, a number times a square root, these are like different types of terms. You can't really multiply them together. You just put them next to one another. That means that they're multiplied together. And then the last example, let's say I have 2 times the square root of 3 times, let's say, 5 times the square root of 7. You multiply what's in front of the square roots, just these integers, 2 times 5, which is 10, and you multiply the square roots together, 3 times 7, that's square root of 21. So you can just think about it as like multiplying like terms. Okay, let's rationalize number 12 now. So we don't want this square root in the denominator, this radical in the denominator. It's considered improper. So what we're going to do is we're going to multiply the numerator and the denominator by square root of 5x. Anything divided by itself is 1, so when we multiply by this fraction, it doesn't change the value, it just changes the way that it looks. So number times the square root, we just put those guys next to each other, and then square root of 5x times square root of 5x is just equal to 5x. So you'll notice when you multiply a square root times itself, you just get the quantity underneath. This is really like 25x squared, but the square root of 25 is 5, and the square root of x squared is x. Here you can see you can reduce a little bit further. These are both just integers. 5 goes into 10 twice. So this comes out to 2 square root of 5x all over x. And you got that one. For number 13, this one's a little bit different because we have a cube root in the denominator. We want to get rid of that radical in the denominator. Notice we have 1, 2. We really need a group of 3 2's. So how many more 2's do we need? We need 2 more. So what I'm going to do is I'm going to multiply the numerator and denominator by the cube root of 2 squared. As long as I do the same thing to the top and the bottom, that's just like multiplying by 1. Now look what happens. 2 to the first times 2 to the second, that's 2 to the third. And the cube root of 2 to the third, these are inverses, you just get 2. Or the way to think about it also is this is like 8, cube root of 8 is 2. In the numerator we have 8 times the cube root of 2 squared, which is just 4. And so now we have 8 over the cube root, or 8 times the cube root of 4, and then the 8 and the 2 we can reduce. 2 goes into 8 4 times. So this simplifies to 4 cube root of 4, and you got that one. Now for number 14, another cube root in the denominator, what can we do on this one? Well, this one we could actually write it as cube root of 8 times the cube root of 2. That's 16. And the reason I did that is because this is a perfect cube. Cube root of 8 is equal to 2. And then we can reduce a little bit. 2 goes into negative 6, negative 3 times. But we still have this issue with the radical in the denominator. So what we can do is, again, we have 1, 2. We need 2 more 2's. So let's multiply by the cube root of 2 squared. That's going to give us 2 cubed. The cube root of 2 cubed is 2. Times 1 is just going to give us 2 in the denominator. And then we have negative 3 cube root of 2 squared, which is 4. And you got it. You can't reduce anything. You can't reduce this one because this is a cube root. This is just an integer. And that's as far as you can go. Okay, for number 15 and number 16, we have a binomial, meaning 2 terms in the denominator. One of them is a radical. We need to get rid of that radical in the denominator. It's considered improper. But when you have a binomial, 2 terms, what we have to do is we multiply by the conjugate. And what the conjugate is, it's the same 2 terms that you see here, 2 and square root of 3, but instead of a minus sign, we're going to put a plus sign in between. Whatever's in the denominator, you want to multiply the numerator by the same thing, because that's like multiplying this whole fraction by 1. If this was a plus, then I'd make both of these minus. So now what we're going to do is we're going to distribute 8 times 2 is equal to 16. 8 times square root of 3 is just going to be 8 square root of 3. Those are different types of terms. We just put them next to each other. Here, though, we have a binomial times a binomial. We have to FOIL, or distribute twice. So 2 times 2 is 4. 2 times square root of 3 is 2 square root of 3. Negative square root of 3 times 2 is negative 2 square root of 3. Notice those cancel because one's positive, one's negative. And negative square root of 3 times positive square root of 3 is just negative 3. Now, whenever you multiply a square root times itself, you get the number underneath, so 3, but a negative times a positive is a negative. Or you could do square root of 9, which is 3. A negative times a positive is negative 3. 4 minus 3 is 1. So anything divided by 1 is itself. So we're just left with 16 plus 8 square root of 3. And you rationalize it. You got rid of that radical in the denominator. For number 16 now, you can see we have 2 radicals in the denominator. It's a binomial. We're going to do that same technique of multiplying by the conjugate, square root of 5 plus the square root of 2. So if this is plus, this would be minus. If this is minus, it's plus. You just change the sign in between. Everything else stays the same. Whatever you do to the denominator, you have to do to the numerator. So now we're going to distribute. Negative 6 times square root of 5 is negative 6 square root of 5. Negative 6 times square root of 2 is negative 6 square root of 2. In the denominator, though, you have to FOIL. But what you'll notice is that the inside and the outside, they cancel. So negative square root of 10, positive square root of 10, that's 0. So we just get the first and the last. So square root of 5 times square root of 5 is 5. Square root of 2 times square root of 2 is 2. But a negative times a positive is a negative 2. 5 minus 2 is equal to 3. And then what I'm going to do now is I'm going to divide both of these groups in the numerator by 3. So negative 6 divided by 3 is negative 2 square roots of 5. And negative 6 divided by 3 is negative 2 square roots of 2. And that's as far as we can go on that one. Okay, for number 17 and number 18, we're talking about adding and subtracting radicals. So how do we add and subtract radicals? Well, you want these radicals to be the same, and then if they're the same, then you can add or subtract the coefficients. So what I mean by that is, let's look at 24. 24 is actually 4 times 6, and square root of 4 is 2. So this comes out to 8 square root of 6. For 54, 54 is 9 times 6. Square root of 9 is 3. So this is coming out to negative 6 square root of 6. So 8 square roots of 6 minus 6 square roots of 6 is 2 square roots of 6. So you can see these radicals are the same. So we're just saying I have 8 of this quantity minus 6 of the same quantity equals 2 of that quantity. Let's look at number 18 now. This one, square root of 75. 75 is like 25 times 3. So this is like 5 times 5, which is 25 square root of 3. Here, square root of 20 is 4 times 5, but the square root of 4 is 2. So this comes out to minus 6 square root of 5. And then over here, 27 is 9 times 3. Square root of 9 is 3. So this is coming out to 6 square root of 3. Now, when we try to combine these, you can see here's a square root of 3, here's a square root of 3. I've got 25 of these plus 6 of these. That's 31 square roots of 3 minus 6 square roots of 5. I can't combine these because I'm not multiplying, I'm just adding or subtracting. In order to add or subtract that square root, that radical has to be the same. So this is as far as we can go on this one. Okay, last two problems. So if you're enjoying this video and you like the way that I explain things, I've got an Algebra 1 and an Algebra 2 video course for sale. I'll put the links down in the description. Check those out if you want to dive deeper into Algebra 1 and Algebra 2, college algebra as well. And if you just want to support the work that I'm doing here on YouTube, consider joining as a channel member for a few dollars a month. You can support this channel, and I really appreciate it. So let's dive into the last two examples. So for number 19, what do we do here? Well, we've got a couple options. We can distribute the square root of 5 into the parentheses, or we could try to simplify what's inside of the parentheses first. So here I notice 243 is actually 81 times 3. So that means that this is coming out to square root of 81 is 9. 9 times 3 is 27. So this is minus 27 square root of 3. 6 square root of 3 minus 27 square root of 3 is negative 21 square root of 3. And then now you can see we're multiplying these together. This is really like a 1 here, 1 square root of 5. So we multiply the numbers together. 1 times negative 21 is negative 21. We multiply the square roots together. 5 times 3 is 15. We can't pull any perfect squares out of 15. It's just 3 times 5. So that's as far as you can go on that one. And for number 20, we have a binomial, two terms, squared. Now, some students make the mistake of just squaring both of these terms. But when it's a binomial like this, you have to think of it as the same quantity times itself. So you've got like two of these groups multiplied together. When you have a binomial times a binomial, you want to FOIL it or distribute twice. So let's go ahead and do that. So we've got 3 root 7 times 3 root 7. You multiply the 3 times 3, which is 9. The square root of 7 times square root of 7 is 7. So that's like 9 times 7, 63. Then we multiply outside. Negative 2 times 3 root 7 is negative 6 square root of 7. And then we do the inside, that's going to be negative 6 square root of 7. And then negative 2 times negative 2 is positive 4. Now we just have to combine like terms. 63 plus 4 is 67. Negative 6 root 7, negative 6 root 7, that's negative 12 square root of 7. And that's as far as we can go on that one. So great job if you were able to follow all those examples. If you want more practice working with radicals, I'll put a video right there. Follow me over to that video and we'll get some more practice. I'll see you over there.